Hello, my name is Rosalea Claeys, and I'm going to be discussing the challenges surrounding the installation and use of geothermal power. Here, you can see the different topics that will be covered during the video. From a simple explanation of the term to more detailed discussions of the challenges, this video will contain all that you need to understand the different restrictions that limit the use of geothermal power. Before we discuss the challenges surrounding geothermal power, it is important to have a solid grasp on the concept itself. What is geothermal power? The term itself is self-explanatory. It is electrical power derived from the thermal energy within the Earth. Now that we know what geothermal power is, we can continue on to the basics of how it works. If geothermal uses the temperature of the Earth to create electricity, then it is important to analyze how the temperature at different levels of the Earth behaves. When at the surface of the Earth, when does the temperature change? The answer is very frequently. Throughout the day, as the sun rises and sets, the temperature rises and falls. Throughout the year, as seasons change, the temperature is impacted as well. This changing temperature does not fare well for consistent and predictable generation of electricity. Alternatively, we can analyze the temperature changes deeper within the Earth's crust. As opposed to the surface of the Earth, where the temperature changes at a specific location over time, deeper underground it does not. Within the Earth's crust, the temperature only changes with depth. This consistency and predictability is perfect for geothermal power plants. There are other consistent sources of heat energy, such as heat sources and heat sinks, but it is important to remember that consistency and predictability of the heat source is directly related to the cost and reliability of geothermal power plants. For a better understanding of how geothermal power plants function past turning heat into electricity, we can discuss the simple thermodynamics behind it. The energy is harvested from the Earth through the process of heat transfer. There are three different forms of heat transfer, and only one is primarily used for geothermal power plants. The first form of heat transfer is conduction, or the transfer of heat energy through direct contact. An example of this would be cooking with a stove. The stove heats your pan by placing the pan directly on top of the hot burner. Another form of heat transfer is convection. This is the method primarily used for harvesting geothermal energy. It utilizes fluids, such as water or air, to move heat from one location to another. A common example of this would be a household radiator, which usually use hot water to heat the surrounding air. The last form of heat transfer is radiation, or the transfer of heat through electromagnetic waves. Unlike the first two forms discussed, radiation does not require a physical medium to travel through. This is how the sun is able to heat the entire planet. In short, there are several different methods available for heat transfer, and convection is the most easily applicable to geothermal power. So, power plants use convection. How is that relevant? Geothermal systems specifically use convection to harvest or distribute heat energy from the Earth. Whether the system is harvesting or distributing this energy depends on the design and purpose of a specific power plant. Look at the equation shown on the screen. It shows a simple way to calculate heat energy transfer. Keep in mind that this specific equation is only viable for convection and not the other forms of heat transfer discussed previously. In the shown equation, heat energy is calculated by multiplying the heat transfer coefficient of the fluid by the surface area of the fluid, and then multiplying that by the difference in temperature between the hot and cold fluids. An important note is that the overall temperature does not matter. It is only the difference between the hot and cold temperatures. Using a radiator as an example, just like before, the heat transfer coefficient would be for the water within the pipes, the surface area would be the surface area of the outside of the radiator, and the difference in temperature refers to the difference between the hot water inside the radiator and the cooler air outside of it. This simple equation allows us to make a few conclusions. 1. The fluid used has an effect on the heat energy transferred. 2. The energy transfer increases with surface area. And 3. Heat energy transfer increases with the difference in temperature. Now that we have a solid understanding of how geothermal power works and the thermodynamics behind it, we can analyze the challenges that geothermal power faces. Most of the challenges can be boiled down to two things: location and cost. There are smaller issues that individual plants can face, but nearly every single geothermal power plant needs to deal with problems regarding the location or the cost of the plant. First, we are going to discuss challenges with location. There are very limited locations available for geothermal power plants caused by two main factors, as you can see here. The first factor is the need for a heat source or sink. This is where the change in thermal energy, as discussed previously, comes from, so the heat source or sink is necessary for the construction of a geothermal plant. These can be found near areas with volcanic and seismic activity. Once a location with a heat source or sink is found, the second factor comes into account. The quality of the land determines whether a geothermal power plant can move from theory into reality. There needs to be enough surface area for the plant to be built without the topography interfering. Additionally, the infrastructure has a large impact on the construction of a power plant. Using the United States as an example, there is little land viable for geothermal power plants on the east coast of the country. The vast majority of the land with enough volcanic or seismic activity to result in a viable heat source lies on the western side of the country. This means that it is incredibly difficult to build these power plants outside of the western states, as there is very limited land capable of fueling a geothermal power plant. As opposed to the heat source, the quality of land is more specific. Also, the quality of land can be changed somewhat to better fit the needs of a power plant. To start, surface area is easy to understand. A power plant can't be built on a very small plot of land. Topography is a bit less simple. Simple hills or shallow slopes can be worked with or changed, but rivers, streams, steep hills, or drop-offs can make land entirely unsuitable for the construction of a power plant. Lastly, there is infrastructure. Not only does a power plant need to be connected to utilities such as electricity and water to keep the plant running, it also needs to be connected to send out the electricity once it is generated. A power plant isn't very useful if it loses half the electricity it generated while transporting it to users. Infrastructure can be built for a power plant, but the location determines the extent of new infrastructure required, and it can become very expensive. This moves us on to the other main challenge for geothermal: cost. Geothermal power plants are expensive. But why? The cost of location requirements and construction add up very quickly and make geothermal power plants more expensive to build than other, less environmentally friendly alternatives. Obviously, purchasing land for a power plant is expensive. Additionally, due to the strict land requirements, such as the heat source and viable infrastructure discussed earlier, this land tends to be more expensive. This adds a lot to the cost of a geothermal power plant. In regards to the construction of the plant, it can be broken into two pieces: the plant itself and any infrastructure that needs to be built to sustain it. Both of these can be very costly, resulting in the overall cost of a geothermal plant to be notably higher than non-renewable alternatives, such as natural gas or fossil fuels. In summary, the main two challenges that geothermal faces is location and cost. The location requirements focus on what is necessary to facilitate the heat transfer that is used to generate the electricity, whereas the cost is focused on the machinery necessary to carry out these thermodynamic processes. Thank you for listening, and I hope you learned something new.